right, so just a quick review, basically the same question problems style that we saw last time, just making sure we're on the same page. So I'll give you guys a couple minute head start. Lean on the person next to you, make sure you guys are working together, see what we can come up with.
Is K considered your Z, or would it be?
It is the vector 0, 0, 1.
Okay.
So yes. start to talk about these. So given two vectors, vector v, vector u, I wrote them in two different kinds of notation. I'll be honest, it's kind of silly to do that. You'll never approach a problem and vectors are written in different representations like that. Just doing it in the beginning to exercise remembering this vector component form. If you see ijk, can you just kind of think of that as being an x, y, z component? There is no j hat, so my y component is just 0. First one, this one could have said find the magnitude, find the length of the vector, or it could have written it out symbolically like this. This is the notation saying find the magnitude or the length of the vector. So we flip through our notes and we go, okay, it's the square root of x squared plus y squared plus z squared. So writing this in my vector component form, I've got 3 squared plus 0 squared plus negative 6 squared. I get the square root of 45. For part B, I want 7v minus 2u. Remember that 7v, we're stretching the vector by a length of 7. So to multiply by a scalar, it works out exactly the way we want it to. You just multiply each of the components by 7. Minus 2 times that vector, so I can just distribute my negative 2 through. And then to add two vectors together, you just add the 2 x's, add the 2 y's, add the 2 z's. Please ask questions on A and B. All right, part C, find the unit vector in the direction of V. So just a reminder, we said a unit vector means it's a vector of length 1. So if we want it to point in the same direction as V, then we can just find whatever the length of V was and scale it back by its own length. And anything divided by itself is 1. So that would give me a length of 1. So step 1, just find the magnitude of V. I get square root of 24. And now you can divide each of the components by its length. So you could have written that as 1 over the magnitude as a scalar outside. Distributing that through, this is now my unit vector that points in the direction of V. Questions? So we've seen scaling these vectors, we've seen adding them. We said we can't really subtract them, but we can add the negative of a vector. So the next operation that we need to look at is a form of multiplying these two vectors. So we're going to look at quote unquote the dot product of two vectors. So just given that you have two vectors, vector v and vector u, then vector u dotted with vector v, so we would not read this as times. We would say vector v dotted with vector, u dot v. We are going to multiply the two x components, multiply the two y components, multiply the two z components, and then add all of those together. So we want to make sure that we've got this boxed. So say we have two vectors, vector A, vector B. Then I want to find A dot B, or vector A dotted with vector B is another way you can read that. So looking back at my definition over here, it just says we're going to multiply the two x's, multiply the two y's, multiply the two z's, add it all together. So let's just kind of think about what our answer even means for a second. This is unusual because everything so far, if we wanted to scale a vector by 7, then you still got another vector. If you want to do any other kind of manipulation of it, scale it, then subtracting, you always get another vector. So the very first thing that we notice about this dot product is it gives us a scalar. Which is just a very fancy way of saying it gives us a number now. So vector u dotted with vector b is just going to be a number, like 7 or 17, or in this case we got 0. Vector b dotted with vector a would be -2 times 1 plus 1 times 2 plus 0 times 3. But you still get the final answer of 0. So what you might read is this property that says that the dot product is quote-unquote commutative, which is just a very fancy way of saying it doesn't matter the order in which you do it. A dot B is going to be the same thing as saying B dot A. And so far we're like, okay, well, yeah, I guess, right? But in our next lesson, when we learn about the cross product, we find out that that operation is not commutative. So we do need to keep up with which ones we can change the order of. A dot B is the same thing as B dot A. Questions so far?
So is it always commutative for this case?
The dot product is always commutative. And then the last thing that we want to write down So the dot product by itself, you might be asking, okay, well, what does that number mean? By itself, the dot product really doesn't mean anything. It will be an intermediate step to a lot of different problems that we do. But one of the first properties that we have is if your dot product equals 0, we can say that vectors v and u are quote-unquote orthogonal to one another, which that just means perpendicular. So just thinking about R2 for a second, so two-dimensional vectors. Consider the vector 0, 5. So that's my vector M. Give me any vector that is quote-unquote orthogonal to vector M, meaning perpendicular.
5, 0.
5, 0. I'm going to call that vector N. Now, it did say name any vector. If you said 2, 0, even if you said negative 3, 0, we're still good. Now it says show that they are orthogonal, so I've got that property down there that says if vector v dotted with vector u equals 0, my dot product is 0, then these two vectors are quote-unquote orthogonal or perpendicular. So we said multiply the two x's, multiply the two y's, add them together. Sure enough, the dot product equals 0. So just showing you with the simplest case, you've got one vector along this axis, one vector along another axis. Dot product equals 0. Questions there? So another question you might be asking is, okay, well, if we see vectors that are perpendicular to one another, what would it mean if vectors are parallel to one another? So we can say two vectors are parallel to one another if they are scalar multiples. So go ahead and write this down. This is kind of your formal definition of two vectors that are parallel to one another. And this is saying here that one vector can be written as another vector if you just scale it by some constant, the same constant c. So I'll give us a quick example using the same v. So I have two vectors, vector v, vector u. And we kind of play around with this for a second. And I realize that, oh, okay, everything inside vector v is divisible by 2. And this is kind of the structure that we're seeing. Vector v can be rewritten as some constant times vector u. And that's how we can show that these two vectors are quote-unquote parallel. But let's of course remind us visually what this would even mean. So I have two vectors. I've got the vector 2, 3, and I've got the vector 6, 9. Playing around with this for a second, we realize that, oh, everything's divisible by 3. So I've got 3 times vector v. But remind me, what is this going to look like visually if I have the same vector up here, but scaled by 3?
It's not going the same direction, but it's going to be 3 times longer.
That's exactly it. Pointing in the same direction, but 3 times longer. So this is vector u, which is the same thing as saying 3 times. So just for more room, I'm going to write the same example over here. Sometimes, as we progress in this class, it's not going to be as simple as, oh, I just recognize that there's a 3. These could have ugly square roots, they could have ugly fractions. So we need a clean way of recognizing if they're perpendicular. So here's kind of the trick. Divide each of the components by whatever the first component is. So for this vector, my first component is 2, so I'm going to divide each of the components by 2. 2 divided by 2 is 1, and I get 3 over 2. But since I divided everything by 2, I just have to make sure that I throw it back. Now do the same thing over here. 6 divided by, I'm going to divide by the first component. 6 divided by 6 is 1. Then I've got 9 divided by 6, which is 3 over 2. And I can recognize, these are the same vectors here. So again, what was the point of that? Here, it's kind of nice, you can just tell that, oh, they're both divisible by 2. But again, when we've got square roots, ugly fractions, like we're not looking at clean vectors, a trick you can do is just force it to where the first component is always a 1, divide everything through. Once you've done that, now you can just quickly see, okay, I'm left with the same vector here. So I know they are indeed scalar multiples of one another, which means they are parallel.
Nice.
All right, so the takeaway so far. 2 vectors are parallel if they are scalar multiples of one another. 2 vectors are perpendicular or orthogonal if their dot product equals 0. So this one, I've got 2 different vectors, vector A, vector B, and it is the same B over here, so I'll just rewrite them for n plus 6. So I'll give you guys a second, lean to the person next to you. Part 1, find the value of k inside vector B such that the 2 vectors are parallel to one another. And then part 2, for the same vectors A and B, find a value of k such that these two vectors are orthogonal to one another. Alright, give me a hint. For the first one, how can I find a k such that they are parallel to one another? See?
You can divide like 2 by anything, first one, and then 5 by everything,
Yeah.
fraction.
I like that. So in vector A, I'm just gonna divide everything by 2, which is the first component. So 1, comma, 2, comma, negative 1/2, yep. But if I divided everything by 2, then I have multiply by 2. And for vector B, divide everything by 5. Yep.
And then set negative 1/2 and k over 5 equals to negative, define k.
Totally agree. Well, if they're just scaled versions of each other, I don't care what these values are, then I just want scaled copies of the same vector. Well, that just means that my z components need to be the same. So negative 1/2 needs to equal k over 5. So 2k equals negative 5. Or k equals negative 5 over 2. So these are now 2 vectors in 3-dimensional space that are scalar multiples of one. All right, give me a hint for part 2.
Use dot product.
And what specifically do I need to find as a dot product?
I need to find that makes it easier.
Yes. Yep. I need to show that A dotted with B equals 0. So that means when I do my dot product, multiply the two x's, multiply the two i's, multiply the two z's, add all the components together, then I need to get 0. That means 2 times 5 plus 4 times 10 plus -1 times k should be 0. So 10 plus 40 minus k equals 0.
So K should be 50.
So do we get k equals 50? All right. Quick note. This is just a quick sketch. Say I've got vector v, and I've got vector u. Are vectors v and u parallel to one another?
Are they parallel to 180 degrees out of?
Because the heads are pointing different ways.
So our definition is that they need to be scalar multiples of one another. So if vector u is just the negative of vector v,
180 degrees out of phase.
I just multiplied all my components by -1. These two vectors are parallel to one another. So I don't want you to always think that they're pointing kind of in the same direction. They could be pointing in opposite directions. Our definition is just that they're scalar multiples of one another. All right, take 2 seconds, take a breather, send a text. We got one more thing to look at. So another tool for our dot product. So the dot product will allow us to find the angle between two vectors. So if you give me two vectors and in 3 space, I can always find the angle between the two vectors. And that angle theta is going to be the inverse cosine or arc cosine. And then inside the parentheses, I've got the dot product of the two vectors. Why we needed to see the dot product first. Divided by the magnitude of u times the magnitude of v.
Is that our formula?
Yes. So let's go ahead and try it out. I've got vector v, I've got vector u. Find the angle between the two vectors. So looking at the formula, the pieces that I need the dot product. So maybe the first thing I'll do is find u dot v. I need the magnitude of each vector. So maybe the next thing I'll do is go ahead and find the angle between each of the vectors. So vector v dotted with vector u is 2 times 0 plus 1 times negative 1 plus 4 times 3. And I agree, we get 11. My next ingredient, I need the magnitude of each of these vectors. So I've got the square root of 2 squared plus 1 squared plus 4 squared.
Should our calculator be in degrees?
That's a great question. So it really depends on what the calculator asks for. Since angles right now are going to make more sense to us in degrees, let's put it in degrees. But the question would say, write your answer in radians or in degrees. Please ask questions on just the ingredients so far. I've got the dot product, and then I just took 2 seconds and found the length of each of my vectors here. So now I'm ready to just throw this at a calculator. I'm going to run over to my calculator, put it in degree mode. So I've got inverse cosine or arc cosine of 11 divided by the square root of 10 times the square root of 21, and I get 40.62-ish degrees. Questions then? One of the cool things that notice we never actually saw here was this didn't say you have to be in R3 or R2. It actually is independent of that. Because whether the vector is 3-dimensional or 2-dimensional, you can still find the dot product. Whether the vector is in 3D or 2D, you still get a magnitude of each of the vectors. So you don't have to put, oh, this only works in R3 or R2. Let's do one more for exercise. And let's do one that we know what the final answer should be. Before we even put the pencil to the paper, what should our final answer be?
90 degrees.
Say?
90 degrees.
90 degrees. So go ahead and just run through it, do all the steps. When you hit that final button, your calculator, hit enter in degree mode, and you get 90, you go, whew, I know how to do these problems. Say again. I'll show it just to be explicit, but you don't have to. All right, last thing we have to look at today, direction angles. So in 2 dimensions, when we were looking at reviewing vectors, we talked about the length and the direction of a 2D vector. In 3 dimensions, you can still find the length or the magnitude all the same. You just tweak that formula just a little bit and add the plus z squared. But it's not going to be as straightforward for angles as it was in 2D. We said we have our standard position, meaning starting from the positive x-axis, you can sweep counterclockwise, that gives you the angle of the vector. But in 3D, we've got a vector that can point anywhere. So we need to talk about direction angles. It gives you an angle, or actually it gives you multiple angles that this vector is going to point in. And we're going to have 3 different direction angles. We're going to have an angle of alpha, which is the angle between the positive x-axis and your vector. Beta, which is the angle from the positive y-axis to your vector. And gamma, the angle from the positive z-axis to your vector. So if you're not fully convinced by that picture, the words should kind of allow everything to sink in. We've got 3 different angles going around. I've got a vector that's pointing somewhere in 3 space. I've got 3 angles. The angle from the positive x-axis to your vector, the angle from the positive y-axis to your vector, the angle from the positive z-axis to your vector. Alpha, beta, and gamma. One of your properties that needs to be true is that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma equals 1. This feels very similar to our Pythagorean identity from 2 dimensions, that sine squared alpha plus cosine squared alpha equals 1, kind of along the same path. I am going to post videos to YouTube of the proofs of a lot of this. Like, why is it that the dot product equals 0 if the vectors are orthogonal? So on YouTube, on Blackboard, I'll post YouTube links to proofs for each of these. So why this is going to be important is, if you know 2 of the angles, then you can always find that 3rd direction angle using this. And how to actually find those angles . So if you have a vector, x, y, z, then alpha is just going to be the x component, I should say, arc cosine of the x component over the magnitude of the vector beta is arc cosine of the y component over the magnitude of the vector. And same thing with gamma. So these are the 2 things that we need written down. let's put this in action and see what's going on. So, give me your favorite vector in the first octant.
First octant, 3, 4.
1, 2, 3.
Yeah, 1, 2, 3. So let's see how we do. Take 2 seconds. The wording of the question would say something like, find all 3 direction angles. So our ingredients here, looking at our formula, we just need the magnitude. So just looking back, it says alpha is just the arc cosine of your x component over the magnitude. So I've got arc cosine of x, which is 1, over the magnitude square root of 14. Beta is the y component, so 2 over the square root of 14. And gamma is the z component. So I'm just going to run over to Desmos.
74.5, 57.7.
Wait. You said alpha is what?
74.5,
Okay.
57.7, 36.7.
Does anyone disagree with those numbers? Cool. So I asked you to give me a vector in the first octant just so we can kind of use this as a guide. If I've got the vector 1, 2, 3, then this is saying you have an angle from the positive x-axis of 74.5 degrees, an angle from the positive y-axis, 57.7 degrees, and an angle from the positive z-axis of 36.7 degrees.
Nice.
Questions? Sweet. Someone threw out the vector 1, 1, 1. I want to kind of entertain that for a second. If I've got 1, 1, 1, I have a feeling let's try it.
3 square root.
I'm interested to see if that gives us anything exciting. So what we get? It's all 54.7. 54.
Cool.
So all our angles are identical. So I've got 1, 1, 1 pointing out like this, and I've got the same angle from all of my axes.
Okay. Nice.
All right, so this part's. please ask questions on the front page 1 through 4. So the first one is just exercising, do we understand the dot product? So find vector u dotted with vector v's. The biggest thing to remember is your dot product is a scalar. You're going to end up with a number for the dot product. Number 2, determine if the two vectors are orthogonal to one another. So I just need to remember that property that two vectors are orthogonal if the dot product equals 0. So I just find the dot product. I do get 0, so yes, they are orthogonal. 3 says determine if the vectors are parallel, perpendicular, or neither. It doesn't have to be one or the other. You could have two vectors that are just neither parallel nor perpendicular. Testing to see if they're perpendicular or orthogonal. I'm doing the dot product, and I do not get 0. So they're not perpendicular. To test to see if they're parallel, you just need to show that they are scalar multiples of one another. Again, my trick to you is to just get them to be the same form by making the first component a 1. By the way, it doesn't have to be the first component. I've seen people do this before where they make the last component a 1. It really doesn't make a difference. I'm just going to do the first one. I can divide everything by -4. It's still the same vector, so I just need to make sure the -4 is still present. Vector b, to get the x component a 1, divide everything by -8. And now I can see, these are the same vectors, just scaled by different numbers. So they are scalar multiples of one another. So I can say A and B are parallel because they are scalar multiples of one another. Number 4, find the angle between the two vectors. This is just, I pull out my notes, I find the formula for your angle between two vectors. And we go, okay, that's right. The angle between two vectors is the arc cosine or inverse cosine of u dot v divided by the magnitude of u times the magnitude of v. So my ingredients are magnitude of u, magnitude of w in this case, and the dot product of the two vectors. Drop it into my formula, and I get roughly 176.8 cubic meters. Sweet. All right, let's go ahead and stop there for today. Flipping it over, looking at the other ones. Sketch a vector, find its magnitude, find the direction angles. The last one, if a vector has direction angles alpha and beta, how can I find the third direction? That's exactly it. You can find cosine of pi over 2 squared, find cosine pi over 4 squared, subtract it over to pi. Any questions? Sweet. Just a reminder, the solutions are posted to Blackboard. Take time over the weekend, and I will see you guys on Monday.